Okay, good morning all. Thank you all for being here. So we'll discuss about virtual threads and continuations. So virtual threads, as we all know, have been added as a final feature in Java 21. And they bring high scalability to Java. But the real hero of the story is continuations. So continuations is actually the magic that empowers virtual threads to provide high scalability. And that is exactly what we are going to see in this talk. But before we begin, I want to take a quick look in the audience and do maybe a quick poll. So please raise your hand if you are using Java 21. It doesn't have to be production, but it could be a simple app that you created. Let's say 50, 60% of the room. That's good. Thank you. So all the people who raise their hands, they have the possibility to use virtual threads. So now raise your hand if you are using virtual threads in production or maybe a simple application. Well, that's really low. 10% or maybe less. Okay, that could be more. But thanks for participating in the poll and raising your hands. So in this talk, well, actually, this talk is divided in 3 parts. In part 1, we get a little introduction to virtual threads. And then in part 2, we'll look at continuations, what continuations are, how they work, and what are they useful for. And then we will use that understanding of continuations to create a simple version of a virtual thread class. So there will be a lot of live coding. So let's get started. But first, a very quick intro about me. My name is Balkrishna Rawool. I work for ING Bank. OK, the first part, which is introduction to virtual threads. So what we see here is actually an instance of JVM, which is running on some operating system. And the JVM has a bunch of virtual threads. It also has some platform threads, and OS has some OS threads. So let's start with platform threads. Platform threads are actually a thin wrapper over operating system threads. What that means is when JVM wants to create a new platform thread, it requests OS to create a new OS thread or a kernel thread. And when that thread can be created, only then it creates a new instance of platform thread. And because of that, the platform threads, they map to the OS threads with this one-to-one mapping. Now, creating a platform thread is actually a very resource-intensive task. So you don't want to do that too often. When you're done with the platform thread, you don't want to throw it away, but you want to put it in a pool so that next time when you need it, you can use it from that pool. And therefore, platform threads require thread pooling. Virtual threads, on the other hand, are lightweight user threads. Lightweight meaning they require significantly less memory. And because of that, you can create them in abundance. You can create thousands or even millions of virtual threads, and that makes them highly scalable. There's actually one more thing that makes them highly scalable, and we will see that on the next slide. But also one more thing to notice about virtual threads is that they don't need pooling. Because creating a virtual thread is a very cheap operation. When you're done with the virtual thread, you can just throw it away, and then you can create a new one when you need a new one. So in fact, pooling virtual threads is an anti-pattern. You don't want to do that. Now, what we see here in this picture is that some of the virtual threads are connected to platform threads. Why is that? That is because a virtual thread on its own cannot execute anything. It requires platform thread to execute something. But what about these other virtual threads, which are not connected to any of the platform threads? Well, for those, we have virtual thread scheduler. So this is a newly introduced scheduler along with virtual threads. And what this does is it actually mounts a virtual thread onto a platform thread when a virtual thread requires platform thread, and it unmounts the virtual thread when it does not require platform thread. Now, what would be the scenarios where a virtual thread would not require platform thread? It would be when a virtual thread is waiting for something. Let's say it is waiting for a network resource to be available or database to return something. Now, in all those cases, virtual thread is not doing any processing. It does not require CPU, so it does not require platform thread. So it gets unmounted from the platform thread. And in a typical IO-bound applications, threads spend a lot of time waiting. And all of that waiting can be avoided if we use virtual threads. So because of that, only the virtual threads would be waiting, but not the platform thread, and therefore CPU would not be wasted. So if we use virtual threads, CPU would be highly efficiently utilized, and that makes virtual threads highly scalable. We will see that in action in the later part of this talk, but that is basically the idea why virtual threads are highly scalable. Now, one more thing to notice before we move on from this slide, and that is that the platform threads, they are carrying virtual threads in this entire endeavor of mounting and unmounting, and therefore they are also known as carrier threads. OK, that's a lot of theory. Now let's see some action. Let's create some virtual threads. Now I'm going to head over to IntelliJ, and I will open a new file. I hope the font is big enough to read. There are also, I think, monitors in between for you to read. Shall I increase, or is it good enough? Can we read? OK, we need to increase. OK, let me zoom in a little bit and make it. OK, that might be too big. OK, let's go with this. This is huge. So I hope you can still read it. Yeah? OK, I get a yes, so I will continue. So let's create some threads. Let's start with a platform thread. And with Project Loom, there is actually a new API to create a platform thread. And that is to use thread.offPlatform. And that gives us a platform thread builder onto which we can call start, and we can pass a runnable. In this case, I simply want to print the current thread. So if I do that and if I run this, I should see that it creates a new platform thread like this. OK, so you can imagine a similar way to create a virtual thread. In fact, there is. So this gives us a virtual thread builder. And then if we do start, it gives us a new virtual thread instance, like so. And if you look at the two-string representation of the virtual thread, there are a couple of things we can notice. First of all, this is actually the ID of the virtual thread. And that is unique for each virtual thread. And then this part, which is basically the platform thread onto which this virtual thread was mounted when it executed this statement. So we get some information about the carrier thread as well. There's also a shorthand method. So we can simply do start virtual thread. And that would give us a virtual thread. There's also another way to create, and that is to use an executor service. So let me do that. Executor, this will be executors.new virtual thread per task executor. So what this does is it gives me an executor service, which is not backed by a thread pool. But it gives me a new instance of virtual thread every time I request it. And the way to do that is basically to call executor.submit and submit a task. In this case, again, I just want to print the current thread. So if I do that, this will create a new virtual thread. OK, I can actually create a bunch of these. Now that goes out of the screen. But I'm going to create a bunch of virtual threads. And because I'm using try with resources, what it will do is it will make sure that all these virtual threads are finished before I exit this try block. So let me show the code here. So before I exit the try block, all these virtual threads would be finished. So let me run this and then see what happens. So I get a bunch of virtual threads. And if you look at these IDs, they are all unique. That means all of these are different virtual threads. But for example, here, they are all using the same platform thread. So what is happening here is that this virtual thread got mounted onto this platform thread. And when it was done, it got unmounted. And a new virtual thread got mounted onto the same platform thread. So we see that mounting and unmounting in action here. So the question is, how does this happen? What is it basically that is giving this mounting and mounting? And because this is driving the high scalability of virtual threads, what is it that is giving the high scalability characteristics to virtual threads? And the answer to those questions is continuations. So this is the second part of the talk where we will discuss continuations, what they are, how they work. So let's start with first question, what is a continuation? So a continuation can be viewed as the representation of the current state of the program. Now, your program could be as simple as a sequence of instructions, or it could be a bit more complicated, a bit more sophisticated with nested method calls or nested loops. And then you can take continuation at any point in time in this program, and that continuation object would represent the current state of the program, including the nested method call, including the iteration of the loop that you are at when you took the continuation. So when you take a continuation, your program gets paused there, and then you get a handle to the current state of the program. You can pass that object anywhere in the program, and you can decide to resume from there, and therefore it resumes and goes until the end of the program. So you can think of this continuation object as the rest of the program or rest of the computation. OK, but what is the use of this? Well, using this, it allows us to pause the execution of the program and resume it later. And we will see that in action when we look at continuations in Java. But before that, I want to highlight something. And it is that the continuation API in Java is right now only used internally. So it is not supposed to be used by application developers. For now, it is only used internally and only used to implement virtual threads. But then you might ask, why are we discussing it? What is the point in discussing that? Well, 3 reasons. One is that because it gives us good insights in the behavior of virtual threads. Secondly, it will help us to understand how mounting and mounting happens. Basically, what is it that is driving this high scalability characteristics of virtual threads? And thirdly, because it is fun. So let's see if it is actually fun. And for that, let's look at the continuations API in Java. Again, I'm going to open a new file, continuations demo. And I'm going to create a new continuation. Let's say we get that from a method called getContinuation. And this method returns a continuation object. But hang on. I just said that continuation is an internal API. How am I able to use it in my application? Well, it is because I have asked the compiler to expose everything from the java.base module, which is not a good idea. So this is not recommended. Don't do this for your application code that is supposed to run in production. We are only doing it now because we want to get a feel of this continuation API. We want to explore this API and just play around with it. So for now, it is fine. So let me create a new continuation object. We can do that simply by calling the constructor. And the constructor requires continuation scope and runnable. So let's create a scope. Continuation scope. Continuation scope. For the purpose of this talk, you can think of it as the namespace for your continuation. So, and it requires a string. This string could be anything. It could even be empty. But let's pass demo for now. Let's use the scope here. And it requires a runnable. Let's say our runnable is printing a few things. It prints A, B, and C. And then we simply return the continuation. And then when we get the continuation here, what can we do with it? We can run it. OK, so now let's run this and see what happens. We get ABC printed on the screen. So basically, running the continuation has simply run the runnable. There is nothing fancy going on here. But because this runnable is wrapped in a continuation object, we get certain power. And the power is to pause the execution of the runnable. And the way to do that is to call continuation.yield, and then pass the scope. And I want to do it at two places, so here and here. So now let's run this program and see what happens. Well, when I run this, I see only A is being printed. So what is going on? Running the continuation has actually started running the runnable. It prints A here, and then it encounters this continuation.yield call. So that actually pauses the execution of the runnable. It not only pauses the execution, but it also transfers the control here. So I can actually do something here, and it will do that. So if I do something here, and if I rerun this application, basically prints A, and then does the thing that I wanted to do. But the runnable is paused. How do I resume? I can call continuation.run once again, and then that will resume the continuation. So now it prints A, does something, and then it prints B. And then it goes from the last yield point to the next yield point and pauses here. How do I resume? Well, I run once again, and then it resumes the continuation and goes until its completion. So now the continuation is completed. What if I do run once again? Right? So continuation is completed. I want to run it further. I get an exception saying that the continuation is terminated. So basically, you cannot run the continuation when it is terminated. There is a way to check. There is a method called isDone. We will look at a bit later. But for now, let's run it until its completion. So when I run this, I see how I can basically pause and resume a runnable. So by using a continuation, you can actually pause and resume a runnable. So that is the purpose of this demo. But before we move on, I want to highlight a couple of things. One is that this continuation.yield call, it does not have to happen from the body of this runnable. It could be somewhere in nested method calls. And if that is the case, your execution would pause at that point, and it would transfer the control all the way back to this continuation.run point, in fact, immediately after it. Also, this continuation.run call, it does not have to happen from the body of this method. When you get the continuation, you get handle to this continuation object, which represents the current state. And you can pass that object anywhere in your program. Then you decide to resume there. OK, so this pausing and resuming of runnables, how is it happening? It is happening mainly with the manipulation of call stack. So let's explore that with another example. So here, we're going to look how pausing happens with continuation.yield. For that, we're going to use a very simple example. You have a main method, which calls a method A. A actually creates a continuation object, which runs B. and then it runs the continuation. B is calling C. C is just calling continuation.yield. So that's where the continuation should pause. So let's look at stack memory, which is getting filled from bottom to top, and heap memory, so that we understand how does that pausing happens. So when we run this program, you get a main, you get a new stack frame created on the stack for main, which calls method A, and then that actually creates a continuation object. So we'll see that the continuation object created on heap. And then it runs the continuation, and that starts method B, which calls C, and C is actually doing continuation.yield. So this is the point where the execution of the runnable should pause, and it should transfer the control to method A, because that's the one that did continuation.run, right? So it should pause the execution of the runnable. How does that happen? Well, all the stack frames on the stack from continuation.yield until B, they are moved away from the stack, they are moved to heap, and they are saved inside the continuation object. And on the stack, the top stack frame, which is continuation.run, that returns to method A. So that's how you pause the execution of the runnable, and then you transfer the control to the point where the continuation was started, where the continuation.run happened. OK, so this is about pausing. How is the resume happening? For that, let's look at the same example, but we will extend that a little bit. So we have, again, main, which is calling A, but that, let's say, calls another method called D. So we have A, B, and C as before. And in method D, we are just doing continuation.run. This was the same continuation object that was created in method A. So now let's explore what happens here. Again, we have stack memory and heap memory. And on the heap, we already have this continuation object saved with the stack frames in it. And then on the stack, we have this main method, which was calling method A, right? So this is how it was on the previous slide. So let's resume from there and see what happens. Let's say the method A finishes its execution, and then the control goes back to main, which calls method D. And then D does continuation.run. Now, this is where we should go back to the last yield point and then resume, which is method C. How does that happen? Well, all the stack frames which were saved in the continuation object, they are now put back onto the stack. They are moved to the stack, and then the top stack frame, which is continuation.yield, that returns to method C. So that's how you effectively transfer the control to method C, and then you resume the continuation. OK. So this pausing and resuming of the runnable and this continuation, what is it good for? Well, many things, including these 4 things. So you can use continuation to implement virtual threads and green threads, obviously. But you can also create your own versions of coroutines and exception handling if you use continuations. You can also use them for writing your own generators. Now, in this talk, we are going to explore 2 uses. One is the generator, and the second is virtual threads. So let's start with generator. First, what is a generator? Well, a generator is actually a data structure that allows us to write a function that yields values. Normally, when you have a function, it returns one value. But with generator, it returns multiple values, and not all of them at once. So these values are lazily retrieved. And also, you can iterate over these values by using a loop. For example, here. So here you have a generator which is yielding A, B, C, and then you are looping over them by using a consumer. Now, what is the use of generator? Let's say if you are generating these values after a complex calculation or resource-intensive task, so you don't want to do all of that upfront, right? You only want to do that when it is necessary, and that's when you would use generator. Implementing a generator in Java is not that difficult. You can simply use streams, because streams are lazily evaluated. They deal with multiple values. So it is very easy to implement generators in Java using streams, or using iterators, or collection of suppliers. So it's really easy. But what we are going to do is we're not going to use any of these things. We're going to implement generator using only continuations. So let's see how we can do that. I'm going to head over to IntelliJ, generator demo. So what we want to be able to do is create a generator like this, new generator. So let's create this class, public static class generator. And generator generates values of certain type. Let's say they are of type T. And in our case, we want strings to be generated. So let's make a generator of strings, because this is what we want. We want to yield A, B, and C. And we want to use only continuation. So let's add continuation here, continuation. And continuation requires continuation scope. So let's add that as well. And let's add a constructor. And constructor basically just initializes these things. So new continuation scope with generator. And continuation is just simply new continuation with the scope. And runnable, let's say it is empty for now. OK, and then run the continuation. OK, now what we want is that we want our generator to yield these values, A, B, C. We want to write this logic. Let's say we have a lambda in the constructor, which allows us to write that logic. So we can yield A, B, and C. But that's not how the yield keyword in Java works. So we cannot have implementation exactly same as this. So let's get it as close to this as possible. Let's say we have a yield method, which allows us to pass these strings so that we can yield these strings. And that this yield method is available to us on an object called source. Now, hang on a minute, and this will make some sense. And this source is available to us as an input to this lambda. And I'm going to define a source type here, public class source, and then create a new private member variable here of type source, and then initialize the source here. So source equals new source. And now this lambda is actually a consumer of source, right? So let's add the type here, consumer of source, called consumer. And in the runnable, we simply do consumer.accept and pass the source. So this way, we will basically run this lambda. And now the only thing that is remaining is to basically implement this method. So what we have done so far is that we created this source type with this yield method so that we are able to do this source.yield and pass these strings. And that's it, nothing more. So the important thing is to now implementation of this yield method. So what we want is that the generator to generate these values and then not do anything else, right? So we want to pause the execution. And the way to do that is to call continuation.yield and then pass the scope. Also, we don't want to lose this value. So let's put it in a private member variable called value. So value will be t. And that's it. So this way, we are able to define a generator. Now, let's see how we can use it in a loop, right? We want to also be able to use it in a loop. Let's say we have a couple of methods on the generator called hasNext and next, which allow us to use it in a loop. Now, let's implement these methods. hasNext is not that difficult, because a generator has values as long as the continuation is not done. So we can simply return negation of continuation not is done. And then the next method is again not that difficult. We'll return a t, which is simply returning the value that was stored inside source. So let's add this and get value method. Let's make it private. And here I want to continue the continuation. Again, I can't do anything after return. So let me put this in a temporary variable and then return that here. So this way, I'm able to define the generator and also use it in a loop. I will share the link to the source code so you can take a look later. Right now, not much is visible here. So let's run this and let's see what happens with the generator. So when I run this, I see ABC is being printed here. So what is happening is basically generator is generating these values, and every time it's generating value, the continuation is getting paused. It also transfers the control here, so I can actually do something. And it will do that every time it generates value, like so. And I can also decide to terminate this loop, and that way I only execute the part of the generator that I want and not the rest of it. Now, I wanted to include this example of implementing generator using continuation because I wanted to highlight the fact that continuation is a general purpose utility. So it is useful for virtual threads, but also useful elsewhere. But we are here for virtual threads. So let's move on to the third part of this talk, where we are going to implement continuation, where we are going to implement a simple version of virtual threads using continuations. Okay, and these virtual thread, the class that we'll create, it should satisfy certain criteria, and that becomes the goal of our assignment. And the goals are basically a virtual thread instance should not use CPU or when it is waiting or when it is blocked. And a virtual thread can get mounted on several platform thread during its lifetime, and a platform thread can support several virtual threads during its lifetime. So basically, that many-to-many relationship between virtual threads and platform threads should be evident from our implementation. So these seem like pretty reasonable expectations from our virtual thread class. Let's see how we can design it. So what we'll do is we'll start with this virtual thread class, and we will create a consumer, which is basically which is creating a bunch of virtual threads, which have some blocking calls as well. And then we will create a virtual thread scheduler, which will have a bunch of virtual threads and few platform threads, and it will schedule these virtual threads onto these platform threads. OK, this also looks like a pretty reasonable design. So let's go ahead and implement this, starting with the virtual thread class. So let me go ahead and create this virtual thread class here. New class virtual thread. So a virtual thread, in its most simple form, is nothing but a continuation. Of course, it requires a scheduler to execute it. But if you externalize the scheduler part, what remains in the virtual thread is nothing but continuation. So if we simply add continuation here, we would be done. So let's add that. Private continuation. And continuation requires continuation scope. We know the drill. In this case, I'm going to make it public static final continuation scope called scope, and then initialize it already here called virtual thread. OK, and then I'm going to write a constructor, virtual thread, which would initialize the continuation part, new continuation with the scope. And it requires runnable. Let's say we get the runnable as input to this lambda, as input to this constructor, and then we pass that runnable here. Now, we want also to be able to run our virtual thread. So let's add a method public void run, which would simply run the continuation. And let's add a system out so we can see what is going on. Let's say it says this virtual thread is running on, and then it shows which platform thread it is running on. OK, so that's it. This is actually complete implementation of virtual thread. This is all you need. But I'm going to add one more feature to this. It's called the ID of the virtual thread, which would be very handy later on. And for that, I'm also going to create a private static final atomic integer called counter. So I can basically set the ID starting with a value of 1. And then I'm going to set the ID here using the counter. So counter.get and increment. And I'm going to print the ID here so I know which virtual thread is running on which platform thread. That's it. So virtual thread implementation is done. Now let's create some virtual threads. And for that, I'm going to create a new class called demo. And demo is going to have a main method. And here I'm going to create a couple of virtual threads. So let's say I have these two virtual threads. I just use live template to generate some code. So I've created these two instances of our virtual thread, which is basically printing few things. We can think of these as instructions our virtual threads are executing. Now, we need a scheduler to execute these virtual threads. So let's add that. We'll create a virtual thread scheduler. And now, if you look at this picture here, the scheduler has a bunch of virtual threads and a bunch of platform threads. And it schedules these virtual threads onto these platform threads, let's say in a first in, first out manner. So for that first in, first out manner, it would be handy to have these virtual threads in a queue. So let's create a queue of virtual threads called queue. And this would be a new concurrent linked queue. And for the platform threads, let's use plain old executor service. Executor service, executor, which would be executors.new fixed thread pool of, let's say, 3 threads. And now we want to be able to start our scheduler. So let's add a method public void start, which would run forever. So basically, when you start the scheduler, it runs forever. And what it does is it checks if there is something in the queue. If there is something in the queue, what it does is it picks that thing up. So it does queue.remove, and then it submits it to the executor. So we do executor.submit, and then we simply run the virtual thread on that platform thread. So this is scheduler is just looking at queue, picking things up, and sending them to this executor to execute things. And we would also need a method to add new virtual threads to our queue. So we create this method called schedule, which takes virtual thread and adds them to our queue. OK, so now we can use the scheduler and use it in our demo to run our virtual threads. So let's add a public static final member here called virtual thread scheduler, called scheduler, which will be a new instance of this. And let's run this in its own thread. So we'll create a new thread, scheduler start, and then we will start the thread. And now I can add this virtual thread to this scheduler. So I do scheduler.schedule virtual thread 1 and 2. So now I can run this. What will happen if I run this? Well, there are 2 virtual threads, and the scheduler has 3 platform threads. So each virtual thread can get 1 platform thread and run in its own thread. So let me run this and see if that is what happens. So what it does is actually virtual thread 1 is running on platform thread 1, and then virtual thread 2 is running on platform thread 2. And they are both running parallelly in their own platform threads. What if I want to make them run sequentially? Well, one way to do that is to basically change these number of threads to 1. So when we have only 1 platform thread, there is no other way than to run sequentially for all these virtual threads. So let's see what happens then. So I see that virtual thread 1 is running on platform thread 1. Then it's run until its completion. And then you have virtual thread 2 running on the same platform thread, because there is only 1 platform thread. So that way we can make them run sequentially. But I want to just change this to 3. And now I want to add a blocking call in this equation. So I want to add the virtual threads to execute blocking call. But before that, I want to add one more feature, and that is thread.currentThread. So now what we do is when we do thread.currentThread, we get the currently executing platform thread. But what if we want currently executing virtual thread? Well, for that, I'm going to add a public static member here of type virtual thread called current virtual thread. So what this will do is this will give me a currently executing virtual thread. But I have a question here now, because there is no one virtual thread, right? There are multiple virtual threads currently running. In fact, there is a virtual thread that each platform thread is executing. So each platform thread has its own virtual thread, meaning this variable would have different value for each platform thread. So my question is, what would be the type of this variable? Thread local. Yes. So I can basically change this to thread local. And that would give me a different virtual thread for each platform thread. But hang on. With Project Loom, there is actually a better alternative to thread locals. Does anybody know what is that better? Scoped value, exactly. So I can actually change this to scoped value. Let me use the scope value here. So new instance. And then all I have to do is set the scope value to the right value when I'm running the virtual threads, which would be here. So I can simply change this code here to say when this scoped value is this value, run the virtual thread. So what this is doing is before it runs the virtual thread, it sets the current virtual thread to that particular thread. So we get the handle on the current virtual thread. OK, now with this feature, let's add a blocking call. So when the OpenJDK team worked on virtual thread, they actually added the implementation of virtual thread, but they also made the entire JDK aware of this new virtual thread implementation. So what they did was everywhere where there were blocking calls happening, they made that blocking calls aware of virtual threads so that only the virtual thread is waiting and not the platform threads. Now, we don't have enough time to change the entire JDK for our new virtual thread. So what we will do is we'll add a simulation of this blocking call. Let's call that class waiting operation, because the blocking call is indeed a waiting operation. And we're going to add a method called perform here. So what this method does, it's a public static void method. It says it has 2 arguments, name and duration. So name is the thing that you're waiting for, and duration is the amount of seconds that you're waiting for. It just prints the thing that it is waiting for this duration. And when it is waiting, you don't want a platform thread to execute something, right? So basically, you want to pause the execution. And the way to do that is to call continuation.yield. So this way, we pause the execution, but we also want to resume execution at certain point in time. So let's add that implementation here. There are many ways to basically resume the execution. I'm going to use timer. Timer is not the best thing, but it's good enough for us. So let me just use that. So timer.schedule, and I'm going to schedule a new timer task. And I want to resume that after duration amount of seconds. And I shouldn't forget to cancel the timer here. And now I want to resume the thread. But which thread? Well, it is the current thread which was executing this perform method. So I can get the current virtual thread here. And that would be using basically the virtual thread scheduler dot current virtual thread dot get. So that gives me a currently executing virtual thread. And let me do a static import for it. Also, static import for this. And now I can resume this virtual thread by using our scheduler. So I do scheduler.schedule and pass this virtual thread. Another static import for this. So this way, what this waiting operation does is it basically pauses the execution, and then after the duration, it resumes the execution. So this is our simulation of a blocking call. And now let's use this simulation in our demo. So I want to make sure that the first virtual thread waits for network for 2 seconds, and the second virtual thread waits for, let's say, database for 5 seconds. Now, what will happen when we run this? Again, we have 2 virtual threads, and we still have 3 platform threads. So when we run this, each virtual thread would get their own platform thread and would start executing in their own threads. But after executing the 2 instructions, they will start waiting. Right? So this is the moment when the virtual thread would get unmounted from the platform threads, and then all the 3 platform threads would be available for any other virtual thread. And therefore, when this virtual thread 1 comes back after 2 seconds, it has all the 3 platform threads available. So it can pick any one of them, complete its execution, and then when virtual thread 2 comes back after 5 seconds, it again will have all the 3 platform threads, and it can pick any one of those. So let's see if that is how it works. So when I run this, what I see is that virtual thread 2 is running on platform thread 2, virtual thread 1 is running on platform thread 1, and then they both execute 2 instructions, then they both start waiting. And then virtual thread 1 comes back after the waiting, and it starts executing on platform thread 3. So a totally different platform thread, and then it completes its execution. And then virtual thread 2 comes back after 5 seconds, and it picks up virtual thread 1. Platform thread 1. So let's see what is happening here. It's actually pretty interesting execution. I sometimes have to run it multiple times because of concurrency to get this particular execution. But this is really interesting. So what is happening here is that let's look at this platform thread 1. Because it was executing virtual thread 1 before the waiting. But after the waiting, it is now executing virtual thread 2. So it supported 1 virtual thread. And after waiting, it is supporting a totally different virtual thread. So one platform thread which is supporting 2 virtual threads. And if you look at this virtual thread, which is thread 2, so it was being supported by this platform thread 2, but after the waiting, it is being supported by this platform thread 1. So it was running with 1 platform thread. After the waiting, it is running on a totally different platform thread. So this execution shows that minute-to-minute relationship between virtual threads and platform threads. So basically, the goals that we had set out for our virtual thread have been met. So we have a good enough working solution for our virtual thread. But hang on, we have a virtual thread implementation, right? And at the beginning, we said virtual threads are highly scalable. So we can create them in abundance. We can have large number of them. So let's now turn the heat up, and let's create, if not million, a few thousand of these. And let's put this to test and see how it will behave. Now, with this, what we will have is, let me indent this a bit. So with this, what we'll have is we'll have 1,000 of these virtual threads and 1,000 of these virtual threads. So we have 2,000 virtual threads running on, let me just increase this count to 10 platform threads. So we have 2,000 virtual threads running on 10 platform threads. And let's see what happens. Right? Let's run this. But before I run this, I want to show you one more demo class, which I had already prepared, which is actually, let me put this on the right side. Now, it's a bit difficult with the big font to see, but this is the right-hand side implementation is actually pretty similar to the one on left-hand side. The only difference is that on the left-hand side, I use virtual threads, and on the right-hand side, I use runnables. So here you have 1,000 of these runnables, 1,000 of these runnables, and they do exactly the same thing. So 2 instructions, then delay of 2 seconds, and the second runnable with 2 instructions, delay of 5 seconds. So exactly same as what is happening on the left-hand side. And the scheduler here is also using 10 platform threads, no virtual threads. So what we have here is that on the left-hand side, I have implementation with virtual thread, and on the right-hand side, implementation without virtual threads, so only platform threads. So let me run the one on the right-hand side first to see how it behaves. It runs and runs and runs. It's pretty boring. It's going to take some time, so I'm going to put this on the right-hand side. And while that is running, I'm going to run the implementation on the left-hand side, which is the one with virtual threads. So let me run this. It's get a bit crowdy here. But OK, it runs, and something has happened. Basically, we see this virtual thread with ID 2000, the last virtual thread that we wanted to execute. It has executed its last instructions. Right? So it has basically all the 2000 virtual threads have finished executing all the instructions with all the waiting, while the platform thread implementation, that is still going on. And in fact, on my machine, it takes 15 minutes to finish the whole thing. So you can basically see the power of virtual threads, right? So what is happening here is that with virtual thread, you can actually get much more things done with the same amount of CPU, provided you have sufficient amount of waiting, right? So that is, in fact, the high scalability promise of virtual threads. And this was the last demo that I had. All the source code is at this URL. And if you are interested in some questions, I'm not sure there's not enough time, but you can connect with me on my social coordinates. And if you did like the talk, you can also rate it nicely at this QR code. And while all of you take your phones out and give me a 5-star rating, let me summarize the talk for you. So what we did was that we started with a little introduction to virtual threads. Then in the second part, we got some information about continuation. So we explored continuations to see what they are, how they work. And then in the third part of the talk, we use that understanding of continuations to create a very simple implementation of a virtual thread. And in doing so, in that process, we got good insights in the behavior of virtual threads. We also got to know how mounting and mounting happens. Basically, what is it that is driving this high scalability promise of virtual threads? And I hope it was fun. Thank you.